Hi everyone! In the last video, we've seen how to accelerate the speed of our programs with Pytorch and CUDA. Today we will take it another step further with Torch-TensorRT. Now TensorRT is a software development kit made by Nvidia. It is built upon CUDA and it uses very clever techniques to make our code run much more efficiently. So in this tutorial, we will focus on a machine learning process called Inference. This is where our model is trained, perfected, and it's ready to serve its purpose. Or in other words, ready to make a prediction. And even though this is a beginner's-friendly tutorial, believe it or not, today we will load a pre-trained neural network and we will use it to make predictions on data it has never seen before. Specifically, a picture of my cat. We will also run a speed test comparing PyTorch models running on CPU, on CUDA, as well as on Torch-TensorRT. And yeah, we will learn how to work with all of them. So are you ready? Let's roll. And we will begin by cloning Torch-TensorRT. To do this, we will type inside the terminal git clone https github.com/nvidia/torch-tensorRT, which will copy this official GitHub repository and store it on our computer. Now let's go ahead and hit enter. And once our download is complete, we can then go ahead and navigate to a brand new folder which was created on our computer. We will do this with cd, change directory, and then torch-tensorRT. And here, we will do something a bit different. We will actually run our code in a Docker container, which is quite similar to an Anaconda working environment. But one difference is that Docker containers include all the libraries, APIs, and other dependencies to run a specific application. So we are basically using an isolated working environment, which the developers of the software have already created for us. So in this tutorial, we are accessing it rather than creating it from scratch and installing things inside it. So let's go ahead and install Docker. And we will actually follow the installation guide I've included in the description. So just navigate there and let's do it step by step. So let's scroll down and we will copy this setting up Docker command, which consists of 2 lines of code. So let's press on this copy icon and let's paste it inside our terminal. Now on your end, you guys will be prompted for your password. I already entered mine off camera, so it's not gonna ask me again. Cool. Now back inside our installation guide, we will follow the post-installation actions. And the first thing we'll do is we will create a Docker group. Oh, it's a bit too big. We will copy the very first command and we will paste it in our terminal. Now you can already see I have everything installed. That's why my Docker group already exists. But on your end, you'll obviously see a different message. So once we've done that, we can then go ahead and add our user to this Docker group. So let's copy the second command. And this will basically grant us root privileges. So let's press enter. And back in the installation guide, we will then update these changes we just made with the next command. So new group, Docker. Let's go ahead and run it. And if everything worked, now we can type docker run hello world. And we can do this without adding sudo in front of it. Now, usually sudo is what grants us root privileges, but we already took care of it, so we don't need it anymore. Let's go ahead and press enter and see if it worked. Let's scroll up. And yep, hello from Docker. This message shows that your installation appears to be working correctly. Perfect. Now let's move on. Next, we will install the NVIDIA Container Toolkit. And once again, we will just copy the appropriate command from the installation guide and we will paste it inside our terminal. Additionally, we will also need the NVIDIA Docker 2 package. And to do this, we will first update our apt package with sudo apt-get update. And now we can use it to install NVIDIA Docker 2. So let's type sudo apt-get install-y NVIDIA-Docker 2. And we will also need to restart Docker. So let's do this with sudo systemctl, as in system control, and then restart Docker. Cool, now let's check if everything worked. So back inside our installation guide, we will copy the base CUDA container command, which you can find here. So let's just press on copy, let's paste it. And if you are presented with information about your GPU, everything is perfect and everything worked. Now, on my end, I zoomed in quite a bit, but on your end, you should see something along these lines. Next, it's time to access a Torch-TensorRT container, and I will actually show you two different methods in which you can do so, where the first one is docker build -t torch_tensor_rt -f ./docker/docker file with a capital D and then space and dot. Let's go ahead and run this command. You can actually copy it from the description, and on your end it will take much longer to run, but because I already built this image before, I don't have to wait all this time. And once we build this Docker image, we can then access it whenever we'd like. So all the commands we've used so far, they were just setup. We will not need to repeat them. But the next few commands are very important because we will need to repeat them every time we'd like to access our Docker container. Now, building a container is simply not enough. We also need to run it. And this command is going to be quite long, so instead of typing it, we will copy it from the description of the video. I already done so. So let's go ahead and paste it, and let's give it a run. And perfect! Once you see this workspace hashtag message, that means you are inside the Docker. And we can now go ahead and access Jupyter Notebook. And first, we will navigate to the folder where all the notebooks are saved. We will do this with cd torch_tensor_rt/notebooks. And from here, we can run Jupyter Notebook with Jupyter Notebook -allow-root -IP 0.0.0.0 and we will go for 8888, which is super common. Let's press enter. Perfect. And we can now open this URL and we will replace host name with localhost. Very important. And now we see there are a bunch of really nice tutorial notebooks here, and we will just ignore them at this point of time, and we will create a brand new Python 3 notebook instead. We will call it Inference. And before we move on with the coding, I actually want to show you another method in which you can access a Torch-TensorRT container. So if you run into any issues, we can always try the Nvidia NGC way. Now the link is of course in the description, and this follows an Nvidia Docker 2 installation. So once we have it installed, we can press on tags, and we will select a version from this list. In my case, I'm going to go for the December 2021 version. Let's press on this 3-dot icon and on pull tag. Now we can paste it inside our terminal, and let's give it a run. Perfect. Now back inside our installation guide, we will navigate to Overview, we will scroll below, and we will select whichever command matches our Docker version. Let's go for the first one in my case. And don't run it just yet, because we will need to modify it a bit. Let's paste it. And we will replace x.xx with 21.12, or whichever version you have selected on your end. We will also add a slash in front of container-dir, otherwise we might get an error. And lastly, we will add --net equals host at the very beginning, otherwise our Jupyter Notebook might not run properly. Okay, let's give it a run. Perfect, and we are inside our workspace. Now, to run Jupyter Notebook, we will use the exact same command, so I'll just fast forward it. We will, of course, open this link, and we will once again replace hostname with localhost. And perfect! We are now accessing Jupyter Notebook from a different Docker. Now back inside our Inference notebook, we will begin with the imports. And we will first import Torch, as in Pytorch. Then, from Torch Vision, we will import models, as well as transforms. Let's give it a run. Now the model we will use today is called ResNet 50. It is a state-of-the-art artificial neural network, and its main purpose is to classify images. Now, if you guys are not sure what neural networks are, I actually have a very handy tutorial explaining them in detail. You can obviously find the link in the description and only then come back here. So ResNet was already trained on a huge database called ImageNet, and it can classify 1,000 different categories of animals, objects, body parts, and all kinds of stuff. Now, the best part is we are more than welcome to borrow it for our needs. So let's go ahead and load it with models. resnet 50, and inside a set of round brackets, we will specify pre-trained equals true, because we are interested in the trained version. That's why we do it. Let's go ahead and assign it to model, and actually let's print it right below. Let's give it a run. And if you were curious how neural networks look like, this is an example of an extremely complex one. So that's state of the art for you. And now that we have a neural network, we will also need an image that it has never seen before. Now in my case, I'm gonna use a picture from my personal gallery, and it's just my cat sitting in a pile of flour, looking extremely tough, like he's from the mafia or something. So back in Jupyter's file system, we will create a brand new folder. We will of course rename it, and we will call it Inference. Now let's go ahead and navigate there, and we will press on upload. Here we can select any image we'd like from our computer, in my case image1.jpg. Let's go ahead and upload it, and perfect! We can now go back to our notebook, where we will use the pillow module to load this image. So in the very last cell, we will type from pil, as in pillow, import image with a capital I. Then right below, we will type image.open, and inside a set of round brackets, we will specify the location of this image. In my case, /inference/image1.jpg. Now let's go ahead and assign it to img as an image, and let's, just to make sure everything looks as expected, we will also print it. Now let's run this cell with Shift-Enter, and there you go. Here's our image. But that's not all. In order to use this image for prediction, we will also need to apply a few transformations to it. Now, if you're not sure what transformations are or why we need them, definitely check out my machine learning database tutorial, where I explain it in great detail. So let's start with transforms.compose with a capital C, to which we will pass a list of very important transformations, where the first one is transforms.resize with a capital R, because our image is way too big for ResNet. So let's set it to a much smaller size of 256 pixels, both for the width and both for the height. Additionally, we would also like to slightly crop our image. So let's type transforms.center crop in camel case, where the final image size we pass to ResNet is expected to be 224 pixels all the way around. So if you choose not to crop your image, please make sure you resize it to 224 instead of 256 pixels. Okay? Next, we would like to add transforms.toTensor in camel case as well. Now, this command will convert our image into a multi-dimensional data structure called tensor. I will expand on it in future tutorials, but for now, just imagine it as a special data structure for machine learning. And then lastly, ResNet expects a normalized input, which is basically reducing the range of values without affecting their actual ratios. So for example, we can normalize values between 0 and 100 to values between 0 and 1, where 88 becomes 0.88, and so on. Now, ResNet expects some very specific normalization parameters. So let's just go ahead and copy them from the documentation. I'm going to include this link in the description. So on your end, you guys can just scroll down. And once you find the first transforms.normalize command, let's copy it. And let's paste it back inside our notebook. Cool. Now I'm super happy with our transformations. So let's assign them to a variable called transform. And then we will apply these transformations on our image. So let's type transform, and inside a set of round brackets, we will specify img, which is our image. And actually, let's reassign it to img. So img equals transform img. And just to make sure that everything worked, we will also print the size of this image. So let's type image.shape. Let's give it a run. Perfect. So we can see that we have 3 color dimensions, one for red, one for green, and one for blue. And we also see that our image is now 224 pixels wide and 224 pixels high, which is almost perfect. The only thing we are missing here is something called a batch size. Now, whenever we train a neural network, we expose it to an enormous amount of images. But if we try to feed all these images at once, we will probably run out of memory. It's just way too much data to handle at one go. That's why we separate our data into batches, and then we can load it bit by bit. So it's very common to use a batch size of 32. Sometimes you will see a batch size of 64, but the key note here is that the first dimension of our images, or tensors I should say, must store the batch size. So for example, if we try to feed our current image into ResNet, it would think that we have 3 images per batch, and each of our images has 224 color channels, and so on, which will obviously return an error. So the solution here is to add a brand new dimension storing our batch size. And since we are only dealing with a single example, our batch size will be 1. We can do this with torch.unsqueeze, to which we will pass our image alongside the position of the new dimension we are adding. In our case, that would be 0 because batch size comes first. Now let's go ahead and assign this expression to image_batch. And once we print its shape, we see that we have now added a brand new dimension for our batch size. Perfect! Now let's make a prediction. And in order to do so, we will need to set our model to evaluation mode with model.eval. Next, we will disable the gradients, as in gradient descent, which we have covered not too long ago in a special tutorial. Definitely check it out for more detail. Now, the reason we do this is because we only need gradients for training. We do not need them for inference, and we don't want them to consume memory if it's unnecessary. So let's go ahead and turn them off. We will type with torch.no_grad and a set of round brackets, and then inside this with statement, we can pass our image into our model. So let's type outputs equals model, and in a set of round brackets, we will specify image_batch. Cool. Now, outside this with statement, we will process the outputs and convert them into probabilities. So essentially, we will get a very long list of all the classes our model is familiar with, and the class with the highest probability is exactly what we're looking for. Now, in order to do this, we will need to pass our outputs through something called a softmax function. We can do this with torch.nn.functional.softmax, to which we will pass our outputs at index 0. And as a second argument, we will specify dim, as in dimension, equals 0. Cool. Now let's go ahead and assign this expression to probs, as in probabilities. But a funny thing happens if we try to print these probabilities. What exactly does it mean? So let's go ahead and convert this into human language, and only then we can understand the meaning. So as a preparation step, we will need to get a list of all the class names that ImageNet has to offer. And the reason why we need it is because our model is only familiar with the numeric class values, while what we're actually looking for is their meaning in English. So for example, the name of the class at index 1 is goldfish, while the name of the class at index 2 is great white shark, and so on. And as you guys can probably see, we can find this category name to category number mapping on GitHub. So let's just follow the link I've provided in the description, and let's press on roll. We can now copy this URL from above, and we will combine it inside our notebook. So the first thing we'll do is we will import pandas SPD, and we will then use it to read this URL we just copied. So we will type pd.read_csv, and inside a set of round brackets, we will pass the URL we've copied in a string. Now, as an additional argument, we will also add header equals none. And let's go ahead and assign it to categories. And of course, let's print it in the line below. Now, if you don't have pandas installed, we can simply do this with an exclamation mark pip install pandas. So let's run this cell just in case. I already have mine installed, but I don't think you guys do. Now let's go ahead and run the next cell. Perfect. And we see that all the class names live in the column of 0. So let's just focus on it. We will specify categories in the column of 0. Let's rerun it. Perfect. And now if we specify the index of 1, we should get a goldfish, hopefully. So let's run it. Perfect, that's a goldfish. Let's see index 2, great white shark. Perfect, now let's move on. Okay, we're almost done with inference. So now let's display the top 5 classes of our image, and hopefully they're all cats. So we will begin by creating a variable called topk, which we will assign to 5. Then we will use the torch.topk method to extract the 5 highest probabilities along with the class number they represent. To do this, we will pass probs as a first argument and topk as a second argument, which is basically 5. Now, since this expression returns both the probabilities along with the class numbers, we will unpack it into 2 variables instead of just 1. So the first one, we will call it prob, because probs is already taken, and the second one we will call it class number. Cool, now let's go ahead and print each of these probabilities with for I in range topk. And the first thing we'll do is we will create a local variable called probability, and we will assign it to prob in the index of I.item, which returns each of our probabilities one at a time. Next, we will create another local variable. This time we will call it class_name, and we will assign it to categories in the index of 0, which returns all our class names, but we will also need to specify the particular class number we're looking for, which is given to us by class number in the index of I. And actually, I have a feeling that this returns a tensor. So let's go ahead and convert it into an integer, because whenever we specify an index, it must be an integer. Tensors are a big no-no here. And then we can go ahead and create a very fancy print statement. So we will type print, and we will open a set of quotes where we will specify placeholder 1 with a set of curly brackets, then space, and then another placeholder. Then we will add a .format method, to which we will pass probability as our first placeholder and class name as our second placeholder, without the typos. And actually, let's return it in a percentage form. So instead of 0.88, I want to see 88%. To do this, we will add a percentage symbol right in front of our first placeholder, and we will then multiply probability by 100, and let's round it. So we'll just convert it into an integer. It's a very fast way of rounding something. Cool, now let's run this cell. Hopefully I didn't have any typos. Aha, okay, so it appears that my 100% Albertan cat is actually Egyptian. Amazing. I need to check if he responds to Habibi. Cool, so we see that Tabby has 19%, which is actually another type of cat, I believe. Double check it on Google, please. We also have a tiger cat, which is perfect because my cat is in the size of a tiger. We also have a Siamese cat and carton. What? Isn't it a box or something? But that's okay because we only have 3% here, and I guess because cats like boxes, we can sometimes find them in boxes. Cool, so we officially know how inference works. And if we're only classifying a single image, this technique running on CPU is gonna do the trick. But what if our program is classifying an entire collection of images? Can we really get away without CUDA or Torch-TensorRT? Let's find out. For this, we will use a special benchmarking function, which you can find in the tutorial notebooks we've mentioned earlier. So let's go ahead and open the ResNet 50 example, which is basically an advanced version of my tutorial. You'll see that many of the commands here are completely different, and then it's slightly more complicated. But this one is dealing with 4 different images for prediction rather than 1. So it's definitely worth a check. Now, what we're looking for here is the benchmark utility function. So let's just go ahead and keep scrolling. And once we see this benchmark utility header, we can then go ahead and copy the entire cell below it, cell number 9. And we will, of course, adjust this function for our needs, and I will explain it in great detail. So let's go ahead and paste it in our notebook, and let's have a look. So the name of our speed test function is benchmark, and the only argument it actually requires is the model itself. The rest of the arguments, or parameters I should say, they have default values. So even if we don't provide anything in their regard during the function call, our function knows that it needs to use these values instead. So let's go ahead and adjust them to something a bit more realistic. So instead of 1024 images per batch, we will reduce it to 32 images per batch, which is much more conventional. And then we also notice that this function is dealing with grayscale images because they only have a single color channel, while our images are colorful RGB images with 3 color channels. So let's adjust 1 to 3. And the last parameter I would like to slightly adjust here is the nruns. So let's reduce it to 100. Because we're looking for a quick speed test. This video is long enough already. And then inside the body of the function, the first thing we do is we generate some random values for our input. And we do this based on the input shape we have selected earlier. So essentially, we are generating 32 dummy images, and we use them for our speed test. Then we go ahead and send our dummy images to CUDA, which is something we will need to adjust because we also want to benchmark our CPU. So let's do something very clever about it. Let's add an additional parameter, which we will call device, and we will give it a default value of CUDA. Then, instead of sending our input data to CUDA, we will send it to device. And then in the lines below, we actually have 2 lines that are not really relevant for our example, so let's just get rid of them. And now the fun part begins. So before we even start timing our speed test, we need to warm up our device. So we are basically running our input data through our model 50 different times before our speed test. And the reason why it's 50 is because n warm up equals to 50 by default, okay? And after we are done with warming up our device, we will call the synchronize method. And the reason why we do this is because our CPU doesn't just stop and wait for the GPU to finish its calculations. It keeps running and keeps processing the rest of our code. So with this method, we are asking our CPU to stop and wait. And only after our GPU calculations are done, we can move on with the actual timing. So given the number of nruns we have selected above, our input data will run through our model 100 different times, during which we will measure the average time it takes for our model to make a prediction. And that's pretty much all we have here in this function. I can break it down even further, but I think it's enough information. So let's give this cell a run, and then we can use this function on our model, and we will check exactly how fast it is. So in the cell below, we will type benchmark, to which we will pass our model along with device equals CPU, at least at first. So are you ready? Let's give it a run. Let's find out exactly how fast our model is. Thank you. Okay, so the average batch time is 661 milliseconds, which, I don't know, we don't have anything to compare it to yet, so we don't know if it's a lot, we don't know if it's a little. So let's go ahead and send our model to CUDA, and then we will measure again. To do this, we will type model equals model.to, and inside a set of round brackets, we will specify CUDA. And then right below, we will type benchmark, and this time we will only specify our model because the device defaults to CUDA. Yeah, let's give it a run and see the difference. Shift enter. Oh, okay. That's faster. Wow, you guys. So the average batch time is 23 milliseconds. Let's see exactly the ratio. So we have 661 divided by 23. Wow. Okay, so this is almost 29 times faster. Holy smokes. Okay, so it doesn't make much sense to use the CPU whenever we're predicting an entire collection of images, okay? At least 32 of them, we know for sure. So let's quickly adjust our model, our cat predicting model, to run on CUDA instead. So let's scroll up. We will need to do 2 little adjustments, where the first one is sending our model to CUDA, and the second one is sending our data to CUDA. So whenever we are loading our ResNet model, we will simply add a toCUDA method. We will rerun this cell. We will scroll below. And then after our unsqueeze command, we will also specify toCUDA. And this will send our data to CUDA as well. So let's rerun this cell. Let's also rerun our prediction cell. And then lastly, our results cell. Cool, so you see that the results are exactly the same, but the only difference is we are now getting them 29 times faster. Cool. So that was CUDA. But how about Torch-TensorRT? We started with installing it and we talked about it so much, but we haven't had a chance to experiment with it. Let's do it now. Now, Torch-TensorRT expects a traced version of our model, which is basically a recording of how the model operates. We give it some example input and we trace it as it passes from function to function. To trace our model, we will type traced underscore model equals torch.jit, which I believe stands for just in time, dot trace, to which we will pass two arguments, where the first one is the model itself, and the second one is the example data we would like to provide, which in our case is a list with torch.rand, n as in random number, and we will select the exact same shape as before, so 32 images per batch, 3 color channels per image, as well as 224 pixels both for the width and both for the height. And then lastly, we will send this data to CUDA, because if you guys remember, Torch-TensorRT is built upon CUDA, and that's why we do it. Now let's go ahead and run this cell with Shift-Enter, and perfect. Now we can convert our traced model to a Torch-TensorRT model. So in the cell below, we will type import Torch_TensorRT, of course, and we will create a brand new variable called TRT_model. We can then set it to Torch_TensorRT.compile, and we will pass 3 arguments here, where the first argument would be our traced model, and the second argument would be, actually, I think my head is about to block the rest of the code, so let's just add a few more cells below. Sorry, guys. And the second argument would be inputs, which in our case will equal a list with Torch_TensorRT.input with a capital I, and we will select once again the exact same shape of 32 images per batch, 3 color channels, 224 pixels all the way around. And additionally, we will also specify a second argument of dtype, as in data type, and we will set it to torch.float32, which is a floating point number with 32 bits. That's the official translation. Now let's go ahead and add our last argument, which would be enabled_precisions, and we will set it to a dictionary with torch.float32 once again. And cool, I believe we can give it a run. Let's do it. Awesome, so it looks like we have successfully converted our model into a Torch-TensorRT model, despite all these warnings. Now let's go ahead and check how fast it gets. So in the cell below, we will type benchmark, to which we will pass our TRT model. And once again, we don't need to specify a device because it defaults to CUDA. Let's give it a run. Let's do it. And oh wow, we are getting 13 milliseconds. Holy smokes, you guys. So yeah, it looks like when we run Inference on Torch-TensorRT, it's twice faster than running Inference on a Pytorch model running on CUDA. Holy smokes. Okay, well, we definitely have a winner. Now let's adjust our cat inference for the very last time, and we will get it to run on Torch-TensorRT instead of just CUDA. So let's scroll above. And what we will do is we will copy this prediction cell. We will combine it with our results cell. And now let's copy everything. And of course, let's revert it back just so we don't get confused. And then at the very, very bottom of our code, we will paste what we just copied. And everywhere you see model, we will change it to TRT model. And yeah, I believe that's all we needed to change here. So let's quickly run this cell and check if it worked. Awesome, yeah, so we're getting the exact same results. So yeah, our model is now running on Torch-TensorRT, twice faster than Pytorch with CUDA, and more than 50 times faster than Pytorch with CPU. So good job, you guys. And as a last step, we will also need to download this notebook. So we will press on File, Download As, and we will go for the IPYNB notebook, and we will save it on our computer. Now, the reason why we do this is as soon as we collapse this Docker, our notebook disappears as well. I mean, holy smokes, you guys. I've just noticed something really cool. So it looks like we've passed an image with a batch size of 1 to a model with a batch size of 32, which is a big no-no. We should never do this. And even though we got this error over here, it looks like our output was printed before this error was triggered, which is incredible, you guys. So whenever you design a model, please make sure that the batch size you specify in your model is 100% matched to the batch size of your sample data, okay? It has to be, because this shouldn't be happening. I don't know how we got away with it. This is nothing but magic. Congratulations! Now you know exactly how to load neural networks and how to use them for inference. And the best part is, you've learned about the most advanced and most efficient tools that only experts were using so far. So if you're just starting your machine learning journey, you need to be extremely proud of yourself, because this is beyond impressive. Now, in the next few tutorials, we will focus on some more machine learning benchmarks, and we will see exactly how OpenCL compares to CUDA. Now, thank you guys so much for watching. I really hope you enjoyed this video, and if you did, please give it a like. If you have anything to say, please leave me a comment. If you'd like to be extra awesome, please subscribe to my channel and turn on the notification bell. Also, please share this tutorial with everybody. Everyone you know. Don't skip even one person. Now, thank you guys so much for watching. Once again, I'll see you very soon.